I'm back again and welcome to Connected Particles. For many students and for majority students, this is the hardest topic because sometimes they cannot get idea what connected particles are and in which cases you can consider those particles as connected. So in the next few minutes, we'll discover actually what connected particles are, and basically we will come back to the modeling again because you understand that this is kind of simplification, because indeed if you consider modeling in math or in physics, you come up within some simplifications, because in reality, even if the particles connected or real objects are connected, sometimes you have more complicated picture and more complicated case, so that you cannot consider them as connected particles model. All right, it's right time to reveal all those theoretical bases and physics that lies behind the scene, and also to reveal approach that we're gonna use and apply to the following problems, which are, of course, is gonna be challenging and EP and P levels. Let's get started. So first, we're going to start with approach and formula. So that's why we need to understand in which case we can consider particles as connected. All right, sometimes you might have a system of objects, and each object might be connected with each other, right? So for example, let's consider this kind of snake that consists of 4 parts, and it moves in some way. So you understand that in this case, at each moment of time or at each time instance, each part is moving in different ways. But there is one thing that you still can consider this more complicated object, like several particles connected, as connected particles model. And I'll explain why. So first of all, you understand that each particle connected with each other by some kind of string or thread, or maybe a rope. And if in the case the rope is very light, so the mass of the string is very small, let's say it's much smaller than the mass of each object in the system. Let's say that's going to be object 1 with mass m1, that's going to be object 2 with mass 2, m3 and m4. So it means that for any I, which is the stays for index of mass, the mass of the string is much smaller than any mass of the part of this system. So that you can say that the string is pretty light, so that you don't need to take into account this part. All right, and the second simplification that we're going to use is that this string is inextensible. Basically, you cannot stretch this string. It keeps the size the same, it keeps the length the same. This is the same as for pendulum. Remember, if you have a pendulum that's basically can be represented by a ball which is attached to the ceiling, and you probably slightly push this and then released. Okay, so for example, you hold it, you divide it by some angle, and then you released. From this point, you understand that actually the string that is suspended by can be considered as inextensible. Otherwise, the length will be changing, and it will be more complicated motion. That's the same. So we are going to consider not only the string, not only very light, but also inextensible. Inextensible means length keeps the same, length is constant. So what it means? It means that if the first object moves with some velocity u, object that follows the first one, which is in this case m4, will keep the same speed but probably different direction of the velocity. but the speed is going to be the same. So if you take absolute value or magnitude of u4, that's going to be the same as for u3. So what it means that the speed and acceleration magnitude will be the same for every single particles. However, as you can see, direction in each time, right, each time instance might be different. All right, so where it's still applicable, of course it's still applicable when you have a horizontal plane or horizontal surface and you have two objects with different masses like this. So you have probably the rope, so you apply the force, which might be in general case at some angle, right, to the horizontal plane, like alpha, and those two objects with mass m1 and m2 are connected with the light string. Let's depict the string with the red line, actually pink one. And this string is inextensible. If it's inextensible, it means if m1 has acceleration a and velocity v, in our case, m2 also will have the same parameters. In this case, direction is still the same if you apply the force, because you can consider those two connected particles, m1 and m2, as moving along the same straight line, okay? In this case, you can consider this model as connected particles model, okay? Where two objects in this system are moving along the same straight line, keeping the same kinematic parameters like acceleration and velocity the same, okay? Because the string is inextensible. If it were inextensible, of course, M2 might be lagging for a while. Then it's going to be during braking, it's going to be like falling with faster and maybe with more velocity in comparison with object 1. Okay, so you understand that that's the same as if it's rigid rod which is not compressible, so that the distance between m1 and m2 keeps the same, and every single kinematic parameter like velocity, like acceleration, and also displacement, they will have the same for both bodies within the system. However, in this case, as you understand, direction is different because each part moves in different ways. However, still the magnitude is going to be the same, right? In that case. All right, have a look here. I'll give you more examples. Let's choose, we cannot choose, all right. So let's choose inclined plane. For example, you have inclined plane here with one angle of inclination, and here is going to be another plane with another angle of inclination. For example, let it be alpha, and that's going to be beta. And they're all different. For example, alpha may be 30 degrees, while beta, let's say it's more about like 50. Okay, let it be 50 degrees. And you have two objects on it. So let's take two objects. And let's say object 1 is going to be a small box, while object 2 is going to be maybe a bigger box in mass. It's going to be M1, that's going to be M2. And how they connected? For example, there might be a small pulley that can smoothly turn, and so that they connected like this with one string that goes over that pulley. You understand there are attaching points to two objects, and that's going to be a pulley here, so that this string is, you can consider it as the whole string just going over this pulley. Or it might be, you know, a very smooth corner so that there is no friction. All right. So what can you say? Is it connected particle system or it's not? According to definition, what ALevel says, so they said that connected particles are basically a system of where all parts of the system are moving in the same straight line. However, this is not the case. It doesn't like satisfy this definition because obviously If this object moves downward along this inclined plane, while object M2 with M2 is moving this way, again, you understand that velocities will be different. However, the magnitude of the velocity, i.e. speeds, will be the same for both objects. If this string is inextensible, we still consider that this string is inextensible. However, directions will be different. Let it be V, let it be U, because of different angles, right? And you understand that M2 is moving along surface with angle of inclination alpha, and that's completely different direction. However, still can be, you still can consider those two objects, this couple, as connected particles. Why? Because actually the magnitude of speed will be equal to the magnitude of the speed of object M1, and that's for M2. And what about acceleration? So magnitude of acceleration be the same, because you consider that this string is inextensible. And of course it doesn't have any mass. So mass is very negligible. So the mass of this string is again much less than the mass of any particles within the system. So that's why it's not necessarily that two objects should be moving with the same in the same straight line. They might be moving, as in this case, over different lines and over different directions. However, there should be definitely straight lines. For example, coming back to this, you understand that there shouldn't be any circular motion, because the curvature will give and will basically provide different acceleration, which in this case is going to be tangential and centripetals. So it's more about physics. But if you consider as if each particles of the system is moving in a straight line, so you still can consider this as their connected particles model. All right, I think that's enough with the approach. So I just maybe provide a bit more examples where you can consider them as connected particles. Let's consider a pulley, and this pulley is attached to the ceiling. So it means this pulley, you cannot use this pulley in order to get gain in the force supply, right? You just basically use this pulley in order to change the direction of the force that you apply. Okay, for example, the first case that I can give you an example with the pulley might be as the following. So you have basically two objects attached to it. For example, that's going to be object 1, and this is another string with, let's say, object 2. Okay, and they have different mass, of course, M1 and M2, otherwise they will be in the balance, obviously. So they have different mass, and this string is just goes over, okay? It goes over that pulley like this way. So there is no friction. Friction in the axis of rotation is very small. Friction is small. So can you consider them as connected particles? Of course, yes, if the string is inextensible. So again, inextensible string, so you can consider them as basically connected particles. However, the direction, again, for example, let's say that M1 is greater than M2. In this case, all the system after releasing will go in this way, so that your pulley will be rotating in a clockwise direction, right? If M1 is greater than M2. Okay, you see that both objects are moving in the straight line, vertical lines, right? But in different directions. So again, velocity are different because of the directions, but in magnitude, they're the same. All right, so I think that I can give you one more example with pulley, where the pulley is using just to change directions, similar to what you can see here with inclined planes. So that's going to be case 2. And in case 2, I'll just give you a brief idea how can be done in order to just change direction. Okay, so have a look here. So you have again the pulley which is there. So you have suspension, kind of suspension, and you have one object hanging on it on the string like this, and let's say another object is staying on the horizontal surface like that. So that's going to be object 1, that's going to be object 2. Okay, so two objects with mass m1 and mass m2, and this object is attached to the end of the string, which is again goes over the pulley and goes to another object m1. So in this case, as you understand, you just simply want to change direction of the force that you apply. For example, you apply the force due to the gravity, which is m1g, okay, and this object m1 will be going downwards, and let's say m1 is greater than m2, and there is no friction between surfaces. Okay, so no friction, that means so m1 might be actually less than m2. Anyway, our system will go in this way, in this direction, so object 2 will be moving horizontally. So that means if you wanted just to change direction of the force that you apply an only vertical force, while you actually pass this effort to object m2. That's why you can use this pulley. And again, in this case, different directions, however, because of the inextensibility of the string, you still can consider those two particles as connected particles. All right, I think that's enough in terms of what connected particles are and in terms of the approach. So I may say only that, for example, in case 1, we have two objects m2 and m1, they connected by the string, and you apply some force to the first body. Sometimes it's very helpful to consider those two objects as one single object with a mass m1 and m2. Okay, why you can do that? Because if you don't need to take into account tension force, which are obviously here, the x on each object of the system, if you don't want to consider them, just consider the whole object as, you know, two particles as the whole objects. All right, so you apply the force and this object moves to the right. Okay, but why you can do, by the way, you can apply the third Newton's law, where for every action there should be counteraction, right, or reaction, which is actually in magnitude the same, but it's opposite in direction. So that's why basically those tension force, the x on object 2 and object 1, they will be the same magnitude and opposite in direction. Actually, this outcome you can use only if the mass of the string connected them, or mass of the rod connected them, those two bodies, is negligible small. All right, only then. If you want, I'll prove why is that. You just simply can apply the second Newton's law to this rod or to this string. So ms times a is going to be resultant force. In this case, let it be this as the positive direction. So it will be T2 minus T1. All right. And because of this mass is negligible small, you'll see that this result is 0, and that means T2 equals T1. But this is again only in a case when your connection string or connection rod is negligible small. In most questions, you actually will have this. Only in more complicated questions related to mechanics, to physics, you'll see that this mass is not actually 0. Very interesting problem that I saw, I don't know, maybe a year ago. That was about the chain, which is which is put on the edge of the table, and in this case you can assume that, yeah, they're connected particles, but the problem is that because this part makes the whole chain moving down, every time you'll have change in mass of the hanging part. Like M2 and M1 and M2 every time gets increased while M1 get decreased over the motion. In this case, you still can consider as connected particles, but the problem is the mass is changing. So in this case, probably you need to take into account the mass of connecting, connecting part which connects M1 and M2, but you can skip that and consider as the whole motion because acceleration and speed will be the same magnitude for both objects M1 and M2 for both parts of this chain. But this is more complicated, it's more about physics, not just A-level mass mechanics. Alright, so I hope you got it, and in the next episode we will discuss not only just the conceptual approach, but I'll give you more formulas and maybe more examples. All right, so that's why you'll be ready for more complicated and challenging questions. However, that will be not really hard, trust me, as always. All right, so let's move to the next one.